Alright, so let's consider one of these example problems in classic block and pulley. With the block on the table, a block hanging over the edge, nice pulley here to reduce the friction between. And normally this will accelerate down this way. I'm going to call that way positive. I'm just going to assume that. I don't know which way it's going to go, if there's enough friction to hold it or not, but we'll consider that. So, first things first, let's get some masses. I'm going to call this mass 1. I'm going to call that mass 2. Let's say we have 50 kilograms hanging off the edge here. And let's say this one is only, I don't know, let's say 100 kilograms sitting on the table. Right? So 50 kilograms is going to be pulling that 100 kilograms over the edge, and they're going to move together, move as a whole system. So everything here is going to move together. So when I look at how much mass is moving, I'm going to look at that total mass. Now, anytime we're talking about this, anytime we're considering this, we want to consider 3 steps. Let's move this over here. First things first, forces. All right, get our free body diagram, get those forces out there. Once we do that, we're going to figure out, all right, well, what's our net force on this object? To do that, we're going to add up all the other forces on it, force 1, force 2, force 3, any of the forces, right, so on and so forth. Add all those up and see what our net force is. Only then, once we've done both of those, can we actually go over to Newton's second law and apply that and figure out what's actually going on with this. All right, so that's our goal. That's what we're talking about here. All right, so with that in mind, tuck that into a corner. Keep this guy out here. Let's look at add some forces to our free body diagram here. Let's do those in red. So look at the mass on the table. It has mass. Anything that has mass is going to have weight. So we have m1g pulling down. That's the weight, but it is sitting on a table. So I'm going to assume that there is a normal force here, and I'm assuming the table's not breaking and it's not launching the mass off the table. So these two guys are going to balance each other. So normal force, the weight on the table, those guys cancel out. Now to make this a little more interesting, let's give this some friction here off the back. Now we're just going to choose what this is. I'm going to say that the friction is, oh, I don't know, let's say 10 newtons. Something simple. All right, so we got 10 newtons of friction resisting the motion since it's falling over the edge. All right, so more forces on our system. We have M2 down here. There's going to be a weight for M2. All right, so M2G. And that's pretty much it. Now, we could consider the fact that, yes, there is, the string is pulling this block and the string's pulling this block up, but these guys are internal forces. So there's tension here and there's tension here, right? But these are internal forces. Anytime we have internal forces, we're not going to consider those. I really need to get a stylus for this. I'm writing with my finger and it looks terrible, but we'll make do. Since they're internal forces, we're not going to worry about that right now. If we look at it separately, like if we were to look at, say, like just this one, and apply Newton's laws to just that one, then we'll consider the tension. For right now, we're going to consider the full thing. So, put this back. We're not going to worry about the tension just yet. So we're just consider the forces that don't cancel out here, that are not internal. Okay, let me move this guy up to the corner. I need some space to write. So there's our free body diagram. All right, so we want our net force. Net force, adding up all the forces. Now, normal force and the m1g, the weight of the block on the table, are going to cancel out. So I'm left with m2g, the weight of the hanging mass, minus the friction, or you consider it as a plus and negative because it's in the opposite direction. Right now, my m2g, my m2 is 50 kilograms. G is 9.8, or about 10 meters per second, minus the friction, which we said was going to be 10 newtons, because it's in the opposite direction. So I get 500 newtons, which is the weight, minus 10 newtons, which is the friction. My net force is 490 newtons. That's the actual net force that's pulling our whole system over the edge. That's pulling it all together. Great. All right, so if that's our net force here, I'll shrink that down a bit. Last but not least, I have gotten step 1, I got my free body diagram. Step 2, I've gotten my net force. I add up all the forces here, what doesn't cancel out, what I'm left with. And last but not least, if I want to find the acceleration, my acceleration is going to be the net force, right? Same net force I found before, divided by my total mass, right? My total mass. So if I want to do that, acceleration is equal to the net force, which is 490 newtons. And I want the total mass, so mass 1 plus mass 2. Or if we want to consider the values first, or second, that is, we have 100 kilograms plus 50 kilograms, which is 490 over a total of 150. It's moving all of those. So scoot this up a bit. So my acceleration is 490 divided by 150, and of course I couldn't pick nice numbers, but that's okay. Grab my calculator, divide it out. I get 3.26 repeating, or about 3.27 meters per second per second. That is the acceleration of my system. But again, as we're doing this, we're always thinking about, first things first, free body diagram. After that, add up the net force. Add up all those forces to find your net force. Last but not least, and only then, once you've done all that, can you use F equals ma to actually find your acceleration or the mass or the missing force that you need. That's a classic example of finding acceleration with friction.